So all of this sounds wonderful, I'm sure, to everybody, but why doesn't everyone use LED chips? The big issue in the past has been lack of light volume or lack of intensity. A single LED chip, while it's fairly efficient at converting electrical energy to optical energy, is still only producing a few hundred or 400 or 500 milliwatts of optical output and dissipating maybe 1.5 watts of electrical current. So you need a lot of them. In the past, that meant scattering large numbers of individually packaged LEDs over a fairly broad area to make either a light bar or a light panel. And even then, the resulting intensity of light output was not really sufficient. But by packing 21 chips, and potentially more in the future, into that small area about the size of a dime, or actually a little smaller than a dime, we can get the intensity up to the point where it's competitive with other light sources, but still has all the advantages in terms of spectrum management that LEDs provide. We like to think of this as not an evolutionary improvement in LED technology, but actually a whole different breed of LED-based product, using that patented multi-layer metal carrier to get the light output of 21 chips in that small confined space. So just to compare a little bit, there's the individual LED chips at various wavelengths. In the past, people have made one LED packages, sometimes done larger chips to get more light output, sometimes put as many as 4 LED chips in a package. But then we're trying to push the envelope quite a bit farther and go to 21 chips in that single small package, with an intent to over time get that even higher. Some of the advantages that this means for plant growers with that traditional approach and having to mount lots of individual LEDs over a fairly wide area, you end up having a wide beam pattern out of each of the chips. So that has two negative effects. You're wasting a lot of light out to the perimeter of the panel, and you're also getting uneven distribution of light. So if you're trying to use multiple wavelengths in a big light fixture that looks like a panel, it'll be uneven blend of spectrum at different points below the panel. In our case, because everything looks like it's coming from that same small point, the light's extremely well mixed. We can put 4 or 5 or 6 different wavelengths, and they all look like they're coming from the same source and are blended and mixed very, very homogeneously. And we can also put some effort into a nice custom designed reflector that can give a different shapes of beam patterns out of the light. Our current product uses about a 60-degree total beam angle, 30 degrees on each side, but we can also do much more focused spotlight beams as well as more diffuse beams when that's an advantage. If you're using traditional LEDs on a panel for growing plants, as I said, a lot of the light goes off to the sides. You can maybe capture some of that with reflective partitions and putting walls between your plant growing area, but even then there's a lot of light wasted. And as I said before, different plants underneath that light panel will see different wavelength blends if there's a mix of LEDs used within the fixture. And then in our case, it's different. The light is more focused. When there's less spread of the beam, you end up having less drop off in intensity as you go farther away from the LED itself, from the LED source itself. So the lower foliage on a plant will see almost as much intensity as the upper foliage of a plant. And every plant will see the same mix of wavelengths. I analogize this to sprinkling out of a watering can versus using a hose. It's a very concentrated beam, and when you really want to get good penetration of the light into the foliage of the plant, you need that focused light source. Why Kessil? We feel we bring both depth and breadth of technology to the problem of providing an effective LED light source, all the way from making the chips ourselves in our clean room to packaging them in our unique metal core dense matrix LED. We also design our own electronics and thermal management subsystems to result in the finished product. And to do that, we bring together all the kind of disciplines needed to do that: electronics design, thermal design, material science, optics, as well as mechanics. And we talked about a lot of this already, but by doing that, we're able to use ultra high brightness LED chips with consistent quality, metallized core board carriers that get the heat out the base of the LED very efficiently, dense packaging with a bunch of optical benefits, the ability to use a single high quality and high performance reflector to get better beam focusing, and the ability to modify the beam focusing for different applications. High penetration, but yet in a compact size. So this is our H150 LED grow light. I think I have one here just so you can get a better sense of the size. And this is our magenta model. As I said, our whole, one of our reasons for being is to provide the wavelengths that support plant growth, and none of the wavelengths that don't really contribute much. This is all red and blue wavelengths. There's no green, there's no yellow. This dissipates about 36 watts of electrical power. And in our growth experiments, we found that 6 of these provide comparable plant growth effect compared to high pressure sodium lamps in the 600 watt range, and are sufficient for a 4x4 foot area to provide a high growth environment for most types of plants. We actually have a family of lamps. A purple lamp, which is viewed as kind of a general purpose. It provides a good balance of vegetative growth as well as flowering and blooming. A magenta version, which just has a little more emphasis of red. In our research, a concentration in blue light tends for strong vegetative growth, short internode spacing, bushy foliage, but not necessarily great for blooming. A lot of red output, conversely, supports blooming, flowering, fruit growth, but doesn't necessarily give you strong, robust, very bushy plants. So magenta is a little slanted more towards the blooming focus, whereas purple is more general purpose. We also think that there's a tremendous market for offering red only and blue only lights as boosters. They can be used to make up for the inadequacies of fluorescent lights and metal halide in the red regions of the spectrum, or conversely make up for the lack of blue output with high pressure sodium. So you can kind of fill in the gaps in the spectrum using either red or blue booster lamps in conjunction with other forms of indoor growing lights. And we think there's a tremendous opportunity to develop tailored light sources that are optimized for different types of plants, different types of nutrient mixes, and perhaps even for different times within the growing year. We've got a 2,000 square foot indoor lab space for doing plant experiments, the ability to conduct 20 different light treatment experiments at any given point in time. Josh Puckett, who's our plant biologist, is here tomorrow to give a presentation on this experimentation, and he'll show real data, videos, photos, etc., of a variety of comparisons of LED grow lights instead of other forms of indoor grow lights, as well as in conjunction as boosters. So if you're here tomorrow, 3:45, I believe it is, we'll be presenting that information then. You can also follow us on Facebook. We're Kessil.led. You can watch a bunch of YouTube videos of time action plant growth comparisons, as well as other informative videos on YouTube at Kessil Tube. And we also have a forum, an online forum for people interested in how to grow plants using LEDs called monorad.com forum subsection. So please join us, and also please join Josh Puckett tomorrow. It'll be very informative and interesting, I think. And thank you. Yes, question?